Welcome to this second part of the STRANU workshop. So we will have 6 presentations actually, and between now and 1 o'clock. So try to be on time, please, all of you. So we start with Mark Hilla. Yes, we'll talk about the baryon-baryon interaction in strangeness sector with lossy QCD. This section is all about measuring the interactions which then are needed not only for for the investigation of residual strong interaction, but also for implication for neutron stars. So please, Mark, go ahead.
Yeah, thank you, Laura, and thank you to the organizers for giving me this chance presenting the results. So yes, I'm Marc Illa. I'm a PhD student at the University of Barcelona, working under the supervision of Assumpta Parreño. And the work that we will present today has been done within the MPL-QCD collaboration with all these people. So let's start with a bit of motivation, which is not really needed. But so if we want to study the baryon-baryon interaction at the low energy regime, we cannot use the fundamental theory QCD because at the energies that we want to study, the coupling constant is too large, and then perturbation techniques cannot be used. So then we have to use effective field theories, where now the degrees of freedom are not quarks or gluons, but they are effective. They are, for example, baryons and mesons. And all the physics that we cannot compute directly from the fundamental theory is put inside these content interactions, where the strength is given by these low energy coefficients. And in order to learn about these coefficients, we have to fit them to data. The problem is that for the systems that contain strange quarks, there's very little data. So here, for example, a summary of all the cross sections obtained for all the baryon-baryon channels, elastic and inelastic, containing STRANGENess, and comparing the Nucleon to the rest, we see that there are less points with larger uncertainties. So this is a problem we're constraining these effective field theories. There are new techniques like the Phentoscopy, like here in the spot from Alice, but still the constraints coming from here are quite large, as you can see by the white area. But there are I think there will come more nice results in the future. I think there are some talks after this one that will talk about Phentoscopy, so I'm not gonna give details on that. So let's move directly. So if we cannot use, there is very little experimental data, what we propose is to use Lattice QCD, where it uses the path integral formalism to compute the expectation value of some operator. So here Q and QR are the quarks and antiquarks, A is the gluon field, and S is the QCD action. But this form is not amenable for computation, so we have to do some changes. The first one is that we have to work in a finite volume, and it has to be large enough that our system fits inside. And then we can reach the infinite volume limit by doing several simulations with different volumes and do the extrapolation. Another change that we have to do is we have to discretize the space-time by introducing a lattice spacing here equal B. Here we can also reach the continuum limit by doing several simulations at different lattice distance and then doing the extrapolation. And then finally, another change that we have to do is that we have to work with imaginary time. And the reason for that is that this integral, we want to perform this integral with Monte Carlo techniques. But now this weight here, we see that this is imaginary, not real. So we cannot interpret it as a probability distribution function. So when we do this change, this exponential becomes real. We can identify this as a probability distribution function and use the Monte Carlo technique. So in the end, the expectation value is just the mean value of this operator computed over several large amounts of gauge configurations. The problem that we have with nuclear physics, which is when working with more than one baryons, is that still most of the results till present day are computed with heavier than physical quark masses. There are some that are very close to the physical point made by the HAL-QCD collaboration, but still the rest are performed using heavier than physical quark masses. So why is that? So from the lattice, what we compute are these correlation functions, which in the end, we create the state with the quantum numbers that we want at some initial time, and then we destroy it at some later time tau. And this can be written as a sum of the energies of this system. So if we want to identify the ground state energy, the lowest energy, we can build this effective mass function, which is the ratio of correlator at different time slices. So if we, for very large time, this will plateau to a constant, which is the ground state energy. So here I'm showing two different plots. One is the effective mass plot for the pi, which is series very nice. So in the beginning, we have this excited state contamination, but then as we wait, we reach this plateau, and this is the ground state energy. However, for the nucleon, we see that again, in the beginning, we have excited state contamination, but then where we would expect to see this plateau, we start to see that the noise, the error starts to increase a lot, and we completely lose the noise. So this is what we call the signal to noise problem, which degrades exponentially in time given by this form. The thing is that when we do nuclear physics, meaning more than one body system, this gets even worse since we have this factor A, the number of baryons multiplying in front. So what can we do to circumvent a little bit this problem? Well, we see that this difference at the physical point is around 700 MeV, but if we would use heavy quarks that give a biomass around 800 MeV, we see that this difference gets reduced and it is around 400 MeV. So that is why most of the people do these calculations using unphysical quark masses. However, in the end, we want to reach the physical point to compare with experiments. So what we have to do is increase the statistics. However, to do that, we have to compute more propagators to compute the correlation functions. But the problem is that to compute these propagators, the cost goes as the inverse of the masses of the quark. So using lighter and lighter quarks is telling us that the cost of computing these propagators is going to be more expensive. So another reason why calculations with finite computational time are using unphysical quark masses. Another problem that is independent of the masses of the quark is that when contracting these propagators to form the correlation functions, there's a naive, they scale with a factorial number of the quarks of the systems we want to study. So larger and larger systems are going to be more expensive to compute. There have been some clever algorithms which have reduced slightly this scaling, but still it is very expensive to compute very large systems beyond 4 or 5 body. Nevertheless, there have been some calculations in the regime. So for example, here the MPL-QCD collaboration back in 2013 did a calculation with heavy quarks. All of them have the same mass, which gives a biomass of 800 MeV. So that's the exact SU3 flavor symmetry, and there's no electromagnetic interactions. So they did these calculations for up to 4 body systems with a STRANGeness from 0 to -4. And one thing to point out here, for example, is that they studied these 3 body systems. Like, for example, they found this hypertriton, which is bound also at the physical point, and here it is also bound. They also find that it is bound this lambda NN channel, which is still not sure at the physical point. And then another interesting thing is that they found this 3/2 hypertriton heavier cousin, but it is still also more bound than the hypertriton, and experimentally has not been detected. So I think tomorrow there'll be some talks related to these states, but today I want to focus on two barium systems only in the octet sector. So when we want to study these interactions, we don't get 64 different channels. If we are at the SU3 symmetry point, we get that they are grouped into these 6 different irreducible representations or IREPs. So in a previous study by the collaboration, where they set all the masses to be the same as the physical strange quark, like in the 2013 study, giving a parallel mass of 800 MeV, it's enough to level the systems by the IREP they belong to. However, today I will talk about in this more recent work, where now the light quarks have different mass than the strange quark, but still heavier than its physical value. So now SU3 symmetry, flavor symmetry is broken, and we have a pion mass around 450 MeV. And also the degeneracy inside each multiplet is broken. So we expect that all these channels in principle will behave differently. So in total, we study 9 different channels with strangeness ranging from 0 to -4. So if we want to study these systems at low energies and want to describe them with an effective field theory, we can use for this purpose pionless EFT, which only contains quantum interactions and does not contain meson exchange terms. So at leading order, there are only 6 terms to describe this interaction, and in the end, what we will be able to extract them from the lattice is the combinations for each IREP. So combination C27 is a specific combination of these 6 different coefficients, and the rest for the other variables. Then, next to leading order, we have the inclusion of derivatives from the leading order term, so an additional 6 terms. And then what is interesting is that we can also include the quark mass matrix, which explicitly breaks SU3 symmetry. So we will have additional terms which are not governed by group theoretical arguments. So we have in this case 12. And the interesting thing about this is that they are very difficult to determine with experimental data. So we want to see if with the lattice we can get some information about them or not. Another limit that we want to study is the limit of large number of colors, which Kaplan and Savage predicted that in this limit there's an SU6 spin flavor symmetry. So in this case, only 2 coefficients are needed to describe the whole baryon-baryon interaction. So we want to see if this symmetry holds at the baryon mass that we are studying. So how can we constrain all these coefficients? Well, what we do is that we match them to momentum expansion of the scattering amplitude and leading order. So here A is the scattering length of the 2 baryon channels, and bar is the reduced mass, and here are the coefficients coming from the momentum independent terms. And here mu is a renormalization scale, which depends if our systems are natural or not. So meaning that if they are natural, in principle, they will have the scattering length and the effective range of the same size, and we can set mu to 0. If they are unnatural, like it's the case for the NN channels in nature, where the scattering length is much larger than the effective range, we set it to be the cutoff of the theory, which is around m pi. So now let's see how we can extract this scattering length from the lattice. So this is the setup that we used. There are, as I said before, 2 light quarks, and then there's the strange quark, giving a baryon mass of 450 MeV. Only 1 lattice spacing, so here we have to be careful. We could not study the systematics of finite spacing. What we did was also compute the system with 3 different volumes, so we can do the infinite volume extrapolation. 2 different correlation functions, only this is not important. And then the systems that we study are not only at rest, but also they are boosted, meaning that they have the same momentum, both baryons, and also with back-to-back momentum. So let's start showing the data for the single baryon cases. And since we have explicitly broken SU3 flavor symmetry, we see that the different baryons have different masses, as it should, but still they are heavier than its physical partners. Then this is okay. Then if we move on to study the 2 baryon systems, as I said, when we decrease the masses of the quark, we have this worse signal to noise problem. So now it's not enough to look at the effective mass plot and try to see where there's a constant and fit a constant. So we had to do a more elaborated fitting strategy, which is described here. But then we can extract all the both ground state and excited states energy levels. So this is a summary. So in total, we extracted 12 different kinematic points for each system. And as you can see that while for most of them, the ground state energy, which is the lowest point for the different volumes, is below 0, meaning that there's an attractive interaction, but still we don't know yet if this is a bound state or not, because we have not performed the infinite volume extrapolation. There are some 2 cases like the sigma and cascade spins triplet states, which show that the ground state energies are compatible with 0, meaning that maybe in this case there's a very little attraction or there are repulsive channels. So we expected this behavior for the sigma and spin triplet states, which lives in the 10 era, because in nature it is expected that this channel is quite repulsive. So here we're starting to see this kind of behavior. So for the rest of them, we want to extrapolate to infinite volume to get the binding energy. So we use this, we can do this via the Lucia formalism. So these are the light blue points here. And together with the data extracted at 800 MeV, which is these darker points, we can do some naive extrapolation to the physical point and compare with experimental data or phenomenological or effective theory predictions. So for experimental data, which is mainly the deuteron, our very simple extrapolation is in agreement. And then what is interesting is to compare our predictions with the predictions from phenomenology or effective field theory. So while in most cases they are in agreement, although ours have a very large error bars, there are in some, like for example, the cascade 10 spins triple states, where in principle, our extrapolation would suggest that this system prefers to be bound, while most of the predictions from phenomenology, effective field theory, and even another lattice calculations says that this system in principle is not bound at the physical point. So here we require points closer to the physical quark masses to really make a definitive statement. So this is just exploratory. So this is one usage of Lucia formalism. With that, we can also extract the scattering parameters. So Lucia formalism tells us exactly how to extract specifically the k-cotangent delta in a model-independent way. The problem is that if we want to extract the scattering parameters via an effective range expansion fit, these points have to fall inside the T-channel cut. And for our cases, this is not the case. Not all the points fall inside, so we could use only some of the total of the points. So the extraction of these scattering parameters have quite large uncertainties. So here is a summary for all the channels that we could extract, the scattering length here, the effective range, and the ratio. And looking at the ratio, which is interesting, is that for the cases where we have this ratio resolved, for example, the sigma-sigma or cascade-cascade spin singlet, we see that this ratio is smaller than 1. So in principle, this is signaling that the systems are unnatural. However, but for looking at the coefficients on the effective field theory, we will study both cases, natural and unnatural. So we can then use directly this scattering length to fix the lower G coefficients. But as you can see, these have quite large uncertainties. So another way to extract them is by fixing the scattering length by the binding momenta, which is a relation. This is a relation from coming at leading order. And it is interesting because we can extract the binding momenta with much more precision than from the effective range expansion fits. So first, let's look at the SU3 flavor coefficients. For that, we want to disentangle the symmetry conserving and symmetry preserving ones. And for that, we can only look at the 27 irrep, because in these cases, for the channels belonging to this multiplet, they have the same leading order coefficient. And for the symmetry breaking ones, the coefficients might be the same, but they have different numerical factors in front. So we can disentangle these two contributions. So here, for example, you can see that the gray point comes from fixing these coefficients using the effective range expansion, and the black points comes from fixing the scattering length via the binding momenta, which has much smaller uncertainties. So for the C27 coefficient coming from all the channels are in agreement, which is good. But then if we look at the symmetry breaking coefficients, we see that they are consistent with 0. So mainly this is telling us that SU3 flavor symmetry is still an approximate symmetry, even we have different quark masses. We also see that there are some similarities between the binding energies and scattering parameters within systems that belong to the same irrep. And also we also see that the violation of this Gell-Mann-Okobamba relation is an order of magnitude smaller compared to experimental value. So this is all telling us that SU3 is indeed an approximate symmetry at this biome mass. So once we know that we can work with SU3, we can look at the SU6 predictions, and we can match the leading order SU3 coefficients with the 2 from the SU6. So we can pick different channels to separate the contributions from A and B, as it is done here. And we can see that these extractions coming from different channels are consistent with each other. So we can do a constant fit for all the values and say that SU6 is also an approximate symmetry at this biome mass. So once we have these A and B coefficients, we can do the reverse relation and compute all the leading order SU3 coefficients. So once we have A and B, we're going to compute all the C1 through C6. And here it is interesting to compare our results with the ones coming from 800 MeV. Because as you can see, at 800 MeV, they found that the only important contributing coefficient is the C5.
You have 2 minutes.
Yeah, no, thank you. So here, they found that there's this accidental SU16 symmetry, meaning that only one coefficient is needed to describe the whole baryon-baryon interaction. Now, at 450, we see that still this C5 coefficient is the one that contributes the most compared to the rest, but the others are non-zero, are small but different from 0. So only a remnant of this SU16 symmetry is observed at 450. So as a summary, we have seen that Lattice QCD can be used to constrain effective field theories when there is no experimental data or very few data. And although these calculations are performed not at the physical point, they are very useful to reveal symmetries more clearly. So for example, at 800, they saw that there's this accidental SU16 symmetry. And for 150, we have seen that despite the quark masses having different mass, there's this SU6 and SU3 symmetry that still approximate. Something I have not talked about is that there are discrepancies within different methods, like using variational or Hall QCD. They need to be understood because not all the systematics are still under control. And also, I want to mention that calculations near the physical pion mass are being performed. So stay tuned. In the coming years, we will start to show very interesting results here at the physical point for these STRANGeness systems. So thank you.
So thank you very much, Mark, for this very interesting talk. Are there questions or comments? I will start while people warm up. And I wanted to ask about the scattering parameters that you extract for the Nucleon Xi channel, because you might know or you might not know, but we have measured very precisely this Proton Psi minus correlation function. And in principle, if we have, I mean, from AlQCD, we get normally local potentials that then we can use to, in your case, I guess you don't have local potential when you use your, exactly, but you have scattering parameters as a, let's say, a result. So
yeah,
I was wondering whether you have like, if you could check whether your scattering parameters in the different spin and isospin, let's say, configuration are consistent with our data. In few words, actually, you could maybe provide us the scattering parameters and then we check ourselves whether this is consistent with our data, because we can use the Ledničky-Lyubozhiv formalism to calculate correlation functions with certain scattering parameters. And we could see whether how your results for Xi n, yes, Xi n, and actually now we have also Lambda Xi, as you will see in the talk, in the last but one talk. And it would be interesting to see whether we agree or not.
Yeah, I mean, these are calculations still at 450. They are not the physical point.
I know, but...
And there are no electromagnetic interactions included and all that, but they will be interesting. I don't know if there are other additional channels that you have to include in the Cascade 10 channels, but here we only studied the spin triplet isospin 01. So I don't know if other ones, because this is the only one that doesn't couple to the other flavor channel, so that's why we study this one.
You have other... Yes, one.
So maybe spin singlet channels that couple to other more difficult ones.
No, I mean, yes, you have also singlet. You have both singlet, triplet in spin, and then you have also the isospin combinations. I see. You have only these 3S1.
Yeah.
Still, okay, but but then I ask you something else. If I take for the 3S1 the scattering parameters that you obtain today for sigma n, do they agree with AlQCD?
I think no. I don't think they are in agreement because I don't know about the scattering parameters, but for the binding energies, when we do this extrapolation, I think that they predict that there's no bound state.
Right, but
the
there is no bound state. Actually, experimentally, there doesn't seem to be an evidence of any bound states in this channel. Maybe comparing binding energy is also like too ambitious. Okay, but then let's do like that. Maybe we can compare. So let's say the scattering parameters that, I mean, one can fit to the lattice potential to these and see how they compare. Okay, yeah. Meanwhile, people should be warmed up. Are there any questions or comments? Okay, it doesn't seem to be the case. Thanks a lot. Very nice. No, there is one. Please, Parada, go ahead.
I have a simple question. Can you back to your conclusion? Yeah, in conclusion, you mentioned that Yeah, this one.
Here.
Summary, sorry. In summary, you mentioned that the quark having different mass. Can you explain more about this one? Is that you include the chiral symmetry breaking or what inside?
Sorry, can you repeat the question?
Chiral symmetry, sometimes the people chiral symmetry breaking makes a quark mass different, right?
Yeah.
So in this case, in your lattice calculations, what did you do? So why the quark having different mass?
So we can set the quark masses to be whatever we want. So in this calculation, the one at 450, we set the light quarks to be much lighter than the strange quark. But despite having these different quark masses, which in principle breaks SU3 flavor symmetry, we still see that this symmetry holds. So we see the similarities between binding energies and scattering parameters within the systems belong to the same era.
No, if you if the quark mass is different, but so you take the U and D is the same mass or different?
Yeah,
the same mass. So it means why the quark? It means that what does it mean quark having different masses?
What does it mean having quark different masses?
Yeah. Because for example, for the nucleon, right? You just include the U quark and down quark. But if you include the like a lambda or hyphron, there's a string quark there. So string quark and the up quark have different mass. Exactly, yes. But what do you mean with this one? Do you mean up quark, light quark with the string quark, or just what?
No, we mean that the strange quark is always fixed to its physical value, and then the light quarks we are decreasing. We are decreasing the value, but still not closer to its physical value. So that's why we don't have a pion of 140. We have a pion of 450.
Okay, so nice discussion, but I think that for the sake of time, I have to.
Sorry. Thank you.
No, thanks a lot for asking, and thanks, Mark, for your nice talk. We move to the next presentations, which will tell us about three-body interaction using phentoscopy. So, Raffaele, please go in presentation mode because we see.
Can you see my slides?
Yes, we still have this find. Maybe you can get rid of this window.
Okay.
Yeah, now it's perfect. Go ahead, please.
Okay, so good morning to everybody. Today I will show something very new, namely with Alice, we have the first experimental hint on the three-body strong interaction. This analysis was performed by Laura Scherschnitte. She is a PhD student in Munich, and I contributed by developing a model which is used in the interpretation of the final results. So we investigate the hadron-hadron interaction at the LHC with Alice. At the LHC, we have high energy collision, and in the collision, pair of hadrons are produced at very short distances, and before reaching the detector, the hadrons may undergo final state interaction, and by studying the correlation in the momentum space among the hadrons, we can unveil the underlying strong interaction. And we can test first principle calculation, we can provide new constraint for chiral effective field theories, and also search for new bound state, in particular the baryon bound states. And we are in the non-perturbative region of the QCD. Here, the theoretical calculations are provided by effective field theories and lattice QCD. The models are tested and constrained with the experimental data. And here you see the SU3 interaction puzzle before the phentoscopic studies at Alice. We know very well the nucleon-nucleon interaction experimentally. So in the nucleon sector, we have something on lambda n and on the kaon-nucleon interaction. But for all these in red, nothing or almost nothing was known. We use Alice. Alice is a complex detector system that was built to study the quark gluon plasma, and we want to use it to investigate the hadron-hadron interaction. And this is a kind of challenge. How do we do this? We study high multiplicity events because in high multiplicity event, the strangeness production is enhanced, and ELISE is optimized for the detection of charged particle, proton, kaons, and pions. And we can reconstruct also the hyperons from the weak decay and also from the electromagnetic decays in the case of the sigma zero. So the very good particle identification capabilities of the detector can be seen here. This is the DDX in the TPC versus the particle momenta. And on the right, you see the measured invariant mass that are used to select the lambda. We select the xi, the omega, and also the sigma zero. So how the phentoscopy technique works? We are at the LHC, we have high energy collision, nuclear collision. In the collision, pairs of hadrons are emitted from a common source at very short distances. And before being detected, they undergo final state interaction and then are correlated in the momentum space. This correlation is investigated using correlation functions. Here you see below the famous Koenig-Pratt equation. The correlation function is given as a function of K star. K star is the relative momentum of the pair in the center of mass frame. And it is calculated as a convolution of the emission source, which can be characterized experimentally, and by the square modulus of the wave function. The square modulus of the wave function reflects, of course, the underlying interaction. And from the experimental point of view, we calculate the correlation function, we measure it by using the same event distribution where the two hadrons are emitted in the same collision, and we divide for the mixed event distribution where the two hadrons are emitted into different collisions. So here you see an example on how the phentoscopy works. So we have the first ingredient is the source. We use a Gaussian profile for the source. Here you see R0, which is the source radius, and we plug in an interaction model. We can use directly the wave function provided by the theoretician, or start from an interaction potential and then use our framework CATS to solve the Schrödinger equation and get the wave function. And we calculate the correlation function. So here you see two examples. In the case of an attractive potential with a repulsive core here, we have that the correlation function is almost above the unity, is mostly above the unity. For a repulsive interaction, the correlation function is below the unity. And in case of no interaction, it is flat and equal to 1. The phentoscopic region is this one at low K star. And here the shape of the correlation function is, of course, determined by the interaction, by the modeling of the interaction, but also by the characteristics of the source. And we use the phentoscopy in small colliding systems, namely proton-proton and proton-lead collision at the LHC, because here the typical source radius is of about 1.3 Fermi. Here you see in this plot the shape of the Gaussian distribution of our source. And you see that we have a significant amount of pairs, this area here, that are emitted at very short distances. And this is ideal to test the typical short-range nuclear potential, as you see. And in addition, if the particles are emitted very close to each other, we emulate large baryon densities. So the first ingredient is the source. So we have to determine the source, and this is done using traditional phentoscopy, using the phentoscopy in a traditional way, in the sense that we start from a well-known interaction and we extract the source size. In this case, we use as a benchmark the proton-proton interaction because we know that it is well described by the argon V18 potential, and we cross-checked with the proton lambda using KFT calculation leading order and next to the leading order. In this analysis, we determine the Gaussian core radius as a function of the average transverse mass of the pairs, and we obtain a common source for all the hadron-hadron pairs. Now, from the statistical hadronization models, we know that the proton and the lambda that we detect are not all primordial, only 36% are primordial. The other one are emitted from the decay of strong short-lived resonances, and then we accounted for an exponential tail to the source profile. And here you see the extracted core as a function of the empty bins. And this is for proton-proton in blue, proton lambda next to the leading order in red, and leading order in green. You see that the core radius agrees in all the bin, and this speaks for a common source for the hadron pairs. The analysis here is performed by fitting in each bin, here you see this bin here, the correlation function, this is for proton-proton, with the known interaction, Coulomb, here in this case, Coulomb and argon V18 are used to extract the source radius, and the cross-check, this is our benchmark, and the cross-check is performed using proton lambda. These two, proton-proton and proton lambda, are used because we measure very precisely the correlation function. And as you will see also in the next slide, these are the fundamental ingredient that will be used to extract the genuine three-body correlation. And knowing the empty scaling of the core radius, and we can determine the core radius for all the hadron pairs that we investigate, including also the contribution of the resonances. We have effective Gaussians, where the effective radius, you see, is a bit larger with respect to the core. So we have completely under control the first ingredient, which is the Gaussian, the source to determine the correlation function, and then we can study the interaction. In this talk, I will show the case of the three-body interaction for PPP and PP lambda, and later Maximilian, Georgius, and Emma will show other hadron-hadron interaction cases. So the three-body forces were included in chiral effective field theory's calculation at the next to the leading order to reproduce the properties of bound objects of many-body systems. And the parameters of the model were constrained using binding energy of nuclei and hypernuclei. But here, such measurement yield the superposition also of the two and many-body effects, and the interaction is tested at large distances, because, for instance, in carbon-12, the average distance among the nucleons is of about 2 Fermi. At the LHC, we study the three-body strong interaction in free space, so we are not affected by the by higher order many-body effect. And as I told you, in a small colliding system, we can test very short distances, and then we can test the interaction at very short distances. So the observable in this case is the three-body correlation function. This is obtained by extending the definition of the two-body to the triplets. The correlation function is measured as a function of Q3, not of K star, of course, because we have triplet, and Q3 is the hypermomentum, which is a Lorentz invariant defined here below. And in this slide, you see our measured correlation function in the case of proton, proton, proton on the left and proton, proton, lambda on the right. In the first case, we reconstructed about 1,000 triplets in the phentoscopic region, and in the other case, about 500. So what you see here now are not genuine three-body correlation function. Why? The reason is represented in this cartoon here. In the measured triplet sample, beside the genuine three-body correlation, which is here represented with the blue arrow, we have the pairwise interaction as well. So to access to the genuine three-body correlation, we use the well-established model, well-known model by Kubo, the cumulant expansion method, published in this paper of 1962. And according to the Kubo rule, the genuine three-body correlation, which is also called three-body cumulant, can be extracted from the measured triplet sample by subtracting the lower order contribution in this way. In the lower order, we have the two-body interaction, the two-body correlation, and another particle, the third particle, which is not correlated, and also the uncorrelated sample. Now, if we translate this equation in terms of correlation function, we have the equation here below. We have a phentoscopic cumulant, the measured correlation function, and the two-body correlations. Now, it is crucial to extract the cumulant to evaluate these lower order contributions. And this is done employing two methods. The first one is a data-driven approach. Here we used the same and mixed event distribution. So basically we use the same event distribution for two pairs, and the third one is taken from another event. And from the measured single particle momenta, we calculate the hypermomentum Q3. And on the other side, we have the projector method. Here we use the two-body correlation function for the interacting pair. Here it is the pair 1, 2, which are well known both from the experimental point of view and from the theoretical point of view. And here we perform a kinematic transformation from the K star of the interacting pair onto Q3 in order to project the correlation function from the two-body to the three-body system. The projector is basically the Jacobian of the kinematic transformation. And if we plug in the proton-proton correlation function as a function of K star here, because it is a two-body correlation, we obtain the plot here on the left in the case of proton, 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 and proton, proton, lambda. So these are the projected correlation function. And here you see the comparison with the other method, so the data-driven approach, and you see that they are in very good agreement. With the projector method, the uncertainty are very small, so we have disadvantage. And the same is done for the case of proton lambda. If we plug the proton lambda in this integral, we project onto the Q3 of the PP lambda system. And again, comparing with the data-driven approach, you see that we have a nice agreement also here. So now that we have all the machinery to extract the cumulant, I will show you the result. We can evaluate all the contribution in the Kubo rule. Starting from the measured correlation function, we can then evaluate the genuine three-body correlation. So in this slide here, you see this first part of the cumulant, namely the lower order contribution in the case of proton-proton lambda. And in the plot, you see the comparison for the projected correlation function and the lower order contribution calculated with the data-driven approach. You see that they are in good agreement. Here, there is no genuine three-body correlation. So we have under control this term of the cumulant. And the same here is shown for the case of proton, proton, proton. Again, we have a very nice agreement for the data-driven approach and the projector method. Now, here you see the measured proton-proton lambda correlation function, so this one, compared with the lower order contribution evaluated with the projector method. And the difference between these two correlation functions is basically the cumulant. Okay, so we see that the two correlation function does not agree in this first bin, and when we subtract, we obtain the cumulant. We see that okay, in this first bin the statistics is very low, but so we cannot draw a quantitative conclusion. But if the future run-3 data will confirm this measurement, this speaks for an attractive proton-proton lambda interaction because the cumulant is positive. And now we see the same results for the proton-proton-proton correlation function, the measured correlation function, and the lower order contribution evaluated with the projector method. And here we see a significant deviation from the lower order contributions. And so here we have a significant contribution from the genuine three-body correlation. The depletion in the first two bin indicates, for the case of PPP, a repulsive three-body correlation interaction. And now, again, subtracting, we extract the cumulant that you see here. Here we took into account also for the feed down of the resonances. And in the first 9 bin, the statistical significance is found to be 2.9 sigma. So we have a first hint on the genuine three-body strong interaction. Now we can use our data to test the three-body potentials, and we need then from the theoretician calculation for the three-body scattering. And this, now I go to the summary of my talk. In this talk, I showed the first measurement of the three-baryon correlation function. We extracted the PPP and PP lambda cumulant using the Kubo method. For PPP, we have a signal below 0 indicating for a genuine three-body repulsive interaction. And in the case of PP lambda, we see a signal above 0 indicated for an attractive interaction. With the Ellis run-3 data, we will have a significant increase in the statistics, and we can use now our measured cumulant and correlation function to constrain the theoretical calculation. So we need, from the theoretician, the three-body scattering wave functions. And I thank you for your attention.
So thanks a lot, Raffaele, for being perfect in time and to show us such nice results. And your results, are there questions or comments?
May I ask a question?
Sure, go ahead, Avram.
Very nice results, really original work. But you are restricted here by the isospin. You have 3 protons, so obviously the Pauli correlations are dominant. The question is, how can we get something for PNP, where the PN would be both in I equals 0 and I equal 1 to separate? So perhaps you can do something extracted from PD. At least the Neutron is I equals 0 PN. So you might manipulate on that. I have no clear idea. It's the first time I hear this kind of lecture.
Okay, so thank you very much for your question. So first of all, what we obtained from this analysis is completely model independent, in the sense that we basically subtracted the terms using the Kubo cumulant function method. So what we obtain is really a genuine three-body correlation, which is interaction. But we are also in parallel investigating the proton-neutron correlation function to understand the three-body interaction in the case of PN, okay, in the case where PN are bound in the neutron. So we are analyzing also the correlation function for proton-neutron to extract information, further information on the three-body interaction.
Okay,
thank you.
are there other comments or questions? If it is not the case, thanks a lot, Raffaele. And then we go to the next contribution. That will be Maximilian. So Maximilian will talk about VN, lambda, and sigma coupling channel measured at the LHC. So please, Maximilian, the stage is yours.
Okay, so first I would like to thank the organizers for the opportunity to talk here about constraining the Nucleon lambda, Nucleon sigma coupled channel system using phentoscopy at the LHC. Then, so first I would like to address the question why we should even try to understand these particles. So we have also in the morning heard something about this. So if you think of neutron stars, they are typically very dense objects and a collection of neutrons. So they have a radii between 10 and 15 kilometers. However, they have a mass between 1.5 up to 2 solar masses. And the challenge is here to understand the system and specifically to determine how the equation of state for such system looks like. So in order to exactly determine this EOS, we need to know two things. So firstly, we need to know the chemical composition of the neutron stars. So exactly which particles can live in such an extreme environment. And in order also to answer this question, we secondly also need to know how the interaction among these different constituents look like. We can make an educated guess, and following the line of argument of energetically favorable scenarios, we can try to introduce hyperons to our neutron star, or better to the equation of state of our neutron star. For example, here the lambda and the sigma hyperon. Of course, including hyperons as a new degree of freedom to the system has quite some impacts. And this is seen if you transform your equation of state into a relationship between the radii and the mass of the neutron star. And here in green, you can see the, how this relationship between mass and radius looks like if you assume an equation of state with only neutron matter. So here you have the pure neutron matter curve. As you can see, because the equation of state is quite stiff, we are able to cross this experimentally observed line of 2 solar masses for the neutron stars. I've also indicated here some new results obtained by the NICE experiment. And now if you compare this line with the red line where the lambda hyperon was included, you can see that the equation of state is significantly softer and hence cannot produce such heavy masses. But, and this is the interesting thing, of course, if you include now the lambda hyperon, you should not only care about the interaction between one lambda hyperon and a nucleon, but you should also somehow take into account free body forces. And this was done for in this blue line. So here you can see that including these free body forces significantly stiffens the EOS, and hence you can here see that we arrive at significantly higher masses. But you can also see that somehow modeling this interaction differently produces, again, a much different outcome. And the reason as to why you have here this wide range is because for now, these genuine free body forces are rather poorly constrained from experimental data. So the potential solutions in how we can help theorists to model the equation of state are clear. So firstly, if we can procure high precision measurements of nucleon hyperon interactions, this would already help quite a lot. And also, as you've seen just in Raffaele's talk, if we are able to provide some constraints for the genuine free body forces, where you have the interaction between a nucleon, and a hyperon, this will also help a lot. Okay, then let's now review our knowledge about the proton-lambda interaction and the role of the nucleon sigma coupling. Of course, here I'm not able to show all the experimental efforts which were undertaken in order to understand the proton-lambda system. So I've just here taken one cross-section for this two-body process, lambda proton to lambda proton. And as you can see here, up to now, the uncertainties on the data, especially for the very low momenta, are quite high, and they reach up to 20%. You can also see that while theory predicts this cusp structure, which comes from the opening of the nucleon sigma coupled channel, which couples to the nucleon lambda, could by now not be resolved by experimental data. What's also interesting is that many different theories which were thought of in order to model this process can describe reasonably well this two-body cross-section. However, if we look now here on the single particle potential, which is predicted for the lambda by these several different model calculations, we can see that here these calculations were done for pure neutron matter, and here below you can see the single particle potential as a function of the Fermi momentum, and the Fermi momentum here acts, of course, as a proxy for the density. So you can see here that the average potential that the lambda will feel inside pure neutron matter is quite different depending on which model you pick. And what's also interesting is that if you look now, for example, at the chiral effective field theory, the NLO 13 even has this sign change for the single particle potential, which means at first it is attractive, but then there will, at some density, come a point where actually the interaction between the lambda and the surrounding neutrons will become repulsive. And this is opposite, for example, to the chiral effective field theory, where we have the NLO 19, where we just predict positive, and attractive interaction for the lambda. Okay, then let's move on to the nucleon sigma interaction. So we have quite some data from hypernuclei. We also have some data from the sigma minus atomic. And we also have some data from sigma minus atoms. And as you can see here, the theoreticians were even able to provide some optical potential fitted to this data. However, we can also see here that models which were tuned to all of this data provide us with vastly different values for the single particle potential of the sigma. And what's also interesting is that we even see here that the sign seems not to be clear at all. Now, you've just seen how phentoscopy works in Rafael's talk, so I just want to remind you here that if we are able to fix our source, then we can indeed probe several models which model the interaction of the particle pair of interest. And we can either do this by directly taking a wave function which is provided for us by the theoreticians, or we are provided with some potential. We can then go to the Schrödinger equation and then obtain in this way this two-particle relative wave function in order to model the correlation function. So you've seen that we employ usually this universal source model in order to fix our source. So we take the core, which is then fixed to the average from the average transverse mass of our particle pair of interest. Here you can see it for the proton lambda, and here for the proton sigma 0. And then we add on top the particle specific resonances on this core source. And this are then the effective radii obtained in the case for proton lambda or proton sigma 0. So I've talked previously about coupled channels. So let me go a bit into detail what I mean by them. if you first think of a scattering experiment, then you usually have a well-defined initial and final state. However, these studies were undertaken at the LHC. So at the LHC, we can quite well measure our final state particles, but indeed, we cannot really say what the initial state looked like. And this leads to the so-called coupled channels. So if you think of a different pair of particles, but with matching quantum numbers to your particle pair of interest, then indeed they can end up in the same final state, and then you will measure them. We can observe two threshold effects depending if we are above or below threshold. If the different pair with the same quantum numbers is above threshold, then we will observe some cusp structure, which comes from the opening of this coupled channel at a specific K star. However, should we lie below, we can see that this coupled channel will contribute over this whole range of small K star to our correlation function, and hence we will see an enhancement. The correlation functions I will show you later were obtained with the Alice detector. Here we actually looked at proton-proton collisions at center of mass energies of 13 TeV. The statistics were about 1,000 million high multiplicity events. The reason as to why we look specifically at high multiplicity events is that strangeness is copiously produced in these reactions with respect to minimum bias. So we are able with Alice to directly detect charged particles like protons, cations, and pions. And how we construct the hyperons in question is shown here. So for the sigma 0, it will first decay electromagnetically into a gamma, a low energetic gamma, and into a lambda hyperon. Here the branching ratio is practically 100%. And the lambda is then reconstructed from the subsequent decay into proton pi minus. Here the branching ratio is about 64%. The challenging part about the reconstruction of the sigma 0 is indeed the detection of the very very low energetic gamma. You can see here the central barrier of Alice, and the only way we can actually detect such low energy gammas is by detecting the electron positron pair stemming from pair conversion. In Alice, the pair conversion will take place in the central barrier of Alice. And this is with a probability of conversion of about 8% due to the material budget of the detector. I've also noted down here how many pairs we have and K star smaller than 200. So for the proton sigma 0, we have around 1,100 pairs, and for the proton lambda, we have around 1 million pairs. Mind you, these numbers also include the anti-proton, anti-sigma 0, or the anti-proton, anti-lambda. Now, let me go a bit into detail about the proton lambda analysis. So, of course, our measured correlation function will not only entail our general correlation in which we are interested, but we will also have some contributions, for example, due to purity effects. I will explain this now in the following slides. So first, let's take a look at this purity. So the purity is taken from the invariant mass spectrum of the reconstructed lambdas. And as you can see here, we can fit the distribution with a double Gaussian and obtain a purity of about 95%. Just for completeness, I've also noted down the purity for the protons, which is, however, larger than 99%. Let's first take care of this part of the correlation function. So here we have a proton paired with a misidentified lambda. In order to investigate the shape of the correlation function which this part will produce, we'll make a so-called sidebend analysis. So we pair a proton with a lambda candidate from these sidebands, or essentially a misidentified lambda. Okay, then let me explain the correlation corrected. So the correlation corrected is this term below here. And you've seen here that I've indicated these lambda parameters. So these lambda parameters, they essentially fix how much the correlation with which they are multiplied actually contribute to your signal. The lambda parameters are calculated from single particle properties such as diffraction and the purity. Here I've put the value of the lambda parameters below, and as you can see, we have quite a sizable amount of lambda. We have quite a sizable amount of genuine proton lambda pairs, and but we have also some amount from feed down due to the Xi or the sigma 0. Now the correlations for the genuine correlation as well as the correlation obtained from the feed down with the sigma 0 is modeled using chiral effective field theory, while the correlation stemming from pairing a proton with a feed down lambda obtained from with a feed down lambda from the decay of the Xi is modeled with Hull QCD lattice potentials. Lastly, this term here in front is the non-femtoscopic background, which we also have to account for in the analysis. Then the correlation which you finally see will be the correlation corrected. And here we correct the correlation function for the residual misidentifications, and also we unfold for the momentum resolution. The effect of the momentum resolution is shown here. And you can see that we have some deviation up to 2% with respect to the unfolded experimental data. Now let me come to the result for the proton lambda. So you can see here for the first time the cut structure, which is due to the opening of the nucleon sigma interaction. And you can also see that the in cyan, the fit with the chiral effective field theory prediction for the NLO19, and in red, the fit for the NLO13 potential, and the deviation to the model with respect to the data is shown here below in terms of number of sigmas. And as you can see, the NLO19 is preferred. It's interesting because I've showed you before that the NLO19 actually predicts an enhanced attractive lambda interaction at high densities, but this would require then a more repulsive free-body nucleon-nucleon lambda interaction. We can also see here that the deviations are up to 3 sigma, so there's some room in order to improve the models. So I've previously noted that we are not really sure how exactly the proton sigma 0 looks like. So in order to model this, for now we've used the chiral effective field theory, but you can also try to assume a negligible proton sigma 0 strong interaction. This is shown here. And as you can see, the deviation from the data points to the model is actually smaller in the case where we assume a negligible proton sigma 0 strong interaction. So the data actually prefer this case. Now onto the proton sigma 0 analysis. So as before, our experimental correlation function entails quite a lot of contributions. And here in this case, we also want to study the sidebands, which come from misidentified sigma 0 candidates. You can see that with respect to the previous case, here we have a very large amount coming from this contribution. Here below, you can see the correlation function obtained from the sideband analysis. And the correlation function is then modeled with a Gaussian contribution. This correlation will act as a reference to our genuine correlation, to our full correlation in this study. Here you can see the proton lambda gamma baseline. As you can see, the data are consistent with this baseline, and the data lie a bit above, so they indicate a shallow attractive interaction for the proton sigma 0, and hence a positive sign for the single particle potential of the sigma 0. I would also like to note that this here is really the first observation of the nucleon sigma interaction. Now coming to the summary and the outlook. So I've shown you the very high precision measurement of the proton lambda with a high resolution of the cut structure, which comes from the opening of the nucleon sigma coupled channel. We have seen that the NLO19 is favored. It has an enhanced lambda interaction at high densities. It thus would necessitate a more repulsive nucleon-nucleon lambda interaction. We hope that this data set provides a new impulse in the field for more model tuning of the existing models. and also probed then the free body forces. So I've also shown you the first observation of the proton sigma interaction, where we've seen that we favor a shallow and strong interaction, and we hope that we can clarify the role of the sigma zero within this picture with the much more with the run-free data, where we will have much more statistics. So you've already seen some preliminary look at the proton-proton lambda interaction, and contrary to what we have gained from this study, where we would see that we need some repulsive proton-proton lambda, here we actually see a positive value for the accumulant. So this begs the question how this situation can be eventually resolved. Thank you very much.
Thanks a lot, Maximilian, for this very nice talk about proton lambda and proton sigma interaction measurement. Are there questions or comments? Okay, if this is not then the case, I thank you again, Maximilian. And then we are a little bit ahead even, but I think we can proceed and go to the next talk. I encourage the audience to listen to the talk and ask questions. Otherwise, it's a pity if there is no discussion. So Emma is the next speaker. She will talk about the Proton Phi interaction. Try to talk, Emma.
Can you see the slides?
Yeah,
Hello?
very good.
Does it work? Okay. Okay, so
Yes.
I will start. So in this talk, I want to address the first correlation measurement between proton Phi meson, which is used to study the interaction between these particles from proton-proton collisions with Alice at the LHC. So you've already heard in the previous talks a lot about neutron stars and the equation of state, which depends on the constituents that are considered and interaction among them. So now I will just quickly talk about how the hyperons appear in the neutron star method, because it's relevant for the hyperon star hypothesis. So towards the center of the neutron star, the density increases, and therefore the medium gets compressed. And this leads to an increase in the Fermi energy and the chemical potential. At certain densities, it becomes favorable that nucleons are transformed into hyperons in order to ensure chemical equilibrium. And at even higher densities, where the hyperons become abundant, not only the hyperon nucleon, but also the hyperon-hyperon interaction has to be considered. And about this, I will talk in the following, because it can be treated either directly or as an effective meson exchange. And there, the coupling between the exchange meson and the hyperon is relevant. And in this context, the Phi might play a role because of its nearly pure strange anti-strange content. Some theories predict a repulsive hyperon-hyperon interaction, and the Phi could be the mediator of this strong repulsive force between the particles. And on the right, you can see the mass-radius relation for the neutron star for different Xi single particle potentials, which are calculated from relativistic mean field theories. So the upper branch is with the inclusion of the Phi, and therefore a repulsive hyperon-hyperon interaction, and the lower without. And due to the repulsion, the appearance of the hyperons is shifted to higher densities, and this stiffens the equation of state. And therefore we reach much larger masses. So at least correlation measurement of the proton-Xi interaction, they validate recent high QCD studies, which predict a slightly repulsive Xi single particle potential in the pure neutron matter, which we also find in neutron stars. And therefore, basically these two bold lines are sorted out. And this illustrates what important role the Phi could play in the neutron star, because if we include it as an exchange meson, even the two solar mass neutron stars that have been discovered in the last decade are supported. However, the exact role of the Phi is not that clear because of the lack of experimental data. And yeah, from theoretical calculations, assuming SUT symmetry, it is possible to relate the coupling constant between phi and lambda, basically between the phi and the hyperons, to the coupling constant between phi and nucleon. And therefore, by measuring the correlation function between proton and phi, we indirectly get an access to the hyperon-hyperon interaction in the neutron star. And this might help to pin down the equation of state of the dense hadronic matter. So the correlation function is defined theoretically by the so-called Kunin-Pratt equation. And I will just quickly remind you about that because you've heard the details before. So there are two ingredients. We have the source function, which describes the spatial probability and regulates the particle emission, and the two-particle wave function, which describes the interaction between the particles. And they are both functions of the relative momentum and the relative distance of the particles in the bare rest frame, which is denoted with the star. So experimentally, it can be measured as the ratio between the correlated yield of particles from the same event and the uncorrelated yield, which is obtained from event mixing techniques. And there's an additional normalization constant. So by measuring the correlation function of particles of known interaction, it is possible to constrain the source. And this information can then be used to pin down the unknown final state interaction between proton and phi. Because as you also heard before, the source depends on the specific particle types that go into the correlation function. Just as a reminder, it consists of the Gaussian core from which the particles are emitted, which is then effectively increased by short-lived strongly decaying resonances that feed into the particles of interest. If they have a zeta that is around the core size. So on the right, you can see the core radius as a function of the transverse mass for PP and P lambda pairs. And it decreases with increasing transverse mass, which might be related to the collective effects. And the data for both pairs is in agreement with uncertainties, and therefore we have this universal source model, which can then be used to extract the proton phi source. So by measuring the transverse mass, which is 1.66 GeV, it is possible to obtain the core radius by comparing it to an interpolation of the proton-proton data. And from this, we get a radius of around 1 Fermi. And in the next step, the particle-specific resonances have to be added because they induce an exponential tail to the Gaussian core. And for the phi, there are no relevant contributions. However, there is a sizable amount of strongly decaying resonances that feed into the protons because their primordial fraction is only 1/3. And the main contribution comes from delta resonances. And this leads to an effective Gaussian size of around 1.08 Fermis. And the source is very small, and this gives rise to a pronounced correlation signal. So in this analysis, we employed a data sample from the LHC run 2 data taking period, which lasted from 2016 to 2018. And we used high multiplicity data from proton-proton collisions at the center of mass energy of 13 tera-electron volts. And there are around 1 billion events available for the analysis. And at high multiplicities, there is an enhanced production of particles with hidden and open strangeness. And this is in our favor because therefore we have more phis available, which means a larger pair yield and better statistics. So the LIS experiment provides an excellent particle identification, mainly by employing the time projection chamber and the time of flight detector. And the primary protons are detected directly by ALICE with a purity of 99% and a primary fraction of 82%. And these values are obtained from Monte Carlo simulations. The phi candidates, however, have to be reconstructed from their decay to charged kaons, and the branching ratio is around 50%. However, because the C tau of the phi is very small, around 46 Fermis, which is smaller than the detector resolution, the kaons are treated as primary particles as well, and they are also detected directly due to their charge. So on the right, you can see the resulting invariant mass spectra of the charged kaons with the phi resonance. And yeah, the reconstructed phis have a PT integrated purity of 66%. And here you can see the total yield of proton phi and antiproton phi pairs within the femtoscopic or like within the region where we are sensitive to the strong final state interaction, which is for K star smaller than 200 MeV. So in an ideal world, the experimental correlation function would correspond to the genuine Proton Phi correlation. However, if we look at experimental results, the correlation function takes values larger than 1. And this suggests that actually the interaction between Proton and Phi is attractive. However, in this intermediate K star range, the correlation function is not flat and there is an enhancement. And this hints the existence of additional contributions to the correlation function. And all these contributions have to be accounted for in order to draw a conclusion on the genuine Proton Phi interaction. Therefore, the experimental correlation function is decomposed into 2 parts. So first we have this non-femtoscopic part, which describes the background, which comes from autocorrelations like mini-jets or energy momentum conservation effects, because they lead to an enhancement of the correlation function at large K star and are typically accounted for by a baseline. The second part comes from contributions to the final state interaction. And here we do not only have the genuine Proton Phi pair, but also misidentified and secondary particles, which are not produced in the primary collision. They are quantified by the so-called lambda parameters, which are calculated from the purity and the feedback fractions of the 2 particles. And in the case of Proton Phi, there are 3 parts. So we have the genuine Proton Phi interaction, which contributes with around 46%. Then a flat contribution from misidentified and secondary protons, which accounts with 10%. And an additional large combinatorial background from misidentified Phi mesons. Because as mentioned before, the PT integrated purity is 66% of the Phis. So in the following, I will talk in more detail about the mini-jets and the combinatorial background, because these were the most challenging parts of the correlation function modeling. So the mini-jets are known from other correlation measurements, and they are present in previous meson-meson and meson-baryon analysis, for example, proton K. Here you can see how the transfer sphericity is defined, and they can take values between 0 and 1. So a sphericity of 0 means that we have a jet-like pencil-shaped event, and the sphericity of 1 means that there is a spherical event. And therefore, in order to minimize the contributions from mini-jets, in the analysis, we only used events with sphericities between 0.7 and 1.0, which corresponds to radar spherical events. And the residual background is then described by Monte Carlo simulated data from PITIA 8. So here you can see the background correlation function, which consists of the mini-jets and the baseline, which accounts for this enhancement of the correlation function at larger K star. And yeah, the other contribution I wanted to talk about is the combinatorial background of proton K plus and K minus. And this arises from the fact that the Phis are reconstructed from the invariant mass of K plus and K minus. And as mentioned before, the purity of the Phi is relatively small. And if we only look at the Phis which contribute to the correlation function at low K star, it's even reduced to 57%. So if we basically pair particles within the resonance with the proton, they contribute to the genuine Proton Phi correlation function. However, due to the large background, if entries in this background are paired with protons, they also induce a correlation signal, which mainly consists of 3 and 2 body interactions between proton K plus and K minus. And they can be accounted for by a sideband analysis, as Max already mentioned before. And there we look at the invariant mass intervals to the left and the right of the Phi resonance. And in order to minimize kinematic effects, the width is chosen to be the same for the 3 intervals. So from this, it is then possible to obtain 2 correlations functions for left and right sideband. And the weighted sum of the 2 is then used as combinatorial background of proton K plus and K minus. And the weight corresponds to the relative amount of entries in each half of the phi interval in the background. So as you can see here, the right sideband contributes slightly more to the combinatorial background. Finally, also a residual amount of phi's is accounted for, which comes from the tail of the resonance that extracts into the sideband intervals. And this is accounted for by a renormalization of the lambda parameters. And here you can see the corresponding data-driven correlation function of the combinatorial background. However, we also compared that to the results from the projector method that Raffaele explained before, and up to 500 MeV, they are consistent. So by combining all contributions and accounting for the respective lambda parameters, it is possible to derive this a model for the background. This accurately describes the enhancement in the intermediate K-star range. And from this, it is possible to obtain the genuine correlation function from the data. And here you can see the result. So at low K-star, it takes values larger than 1, and therefore, indeed, an attractive proton Phi interaction is observed. However, the interaction can also be mediated by coupled channels, which share the same quantum numbers as the proton Phi. And there we have the above threshold channels with a pair mass larger than the proton Phi mass. And they can lead to this cusp structure in the correlation function at the opening a K-star in the proton Phi system. So here we have K-star lambda and K-star sigma. However, no such cusp structure is observed, but also our correlation function is not granular enough. And there are additionally the below threshold channels, which effectively increase the correlation function depending on the coupling strength. So in order to obtain more information on the interaction, the scattering parameters are derived by employing the Leniczky-Lioboschitz approach, which is an analytical approach. And there the correlation function is modeled within the effective range expansion and the S-wave approximation. So an isotropic source of Gaussian profile is assumed with an effective radius of R0. And the correlation function depends on the scattering amplitude, which is defined in terms of the effective range and the scattering length of the interaction. And these scattering parameters are spin averaged. So here you can see the result. And in order to account for these inelastic channels, an imaginary contribution to the scattering length is included. And as you can see, the imaginary part vanishes within uncertainties. And this means that the elastic proton Phi coupling is the dominant contribution to the interaction in vacuum. However, our uncertainties are relatively large on the data and also on the scattering parameters, and therefore run a tree will help to get a definite conclusion on these results. However, it is also possible to extract the coupling constant between Phi and the nucleon by assuming a cover type of potential with real parameters. And the correlation function is then obtained by employing the Katz framework, which is a numerical approach where the Schrödinger equation is solved for a given potential. So in this case, the cover type. And here's the resulting coupling constant. And as mentioned in the beginning, it can be directly linked to the hyperon-hyperon interaction in neutron stars. This already brings me to my summary. So this was the first measurement of the proton Phi correlation function. And an attractive interaction is observed, which is dominated by elastic contributions. And also the the coupling constant between Phi and nucleon is extracted, which is relevant for the meson exchange between hyperons in neutron stars. And also the paper is already published on the arXiv and submitted to PRL.
Thanks a lot, Emma, for these new results on proton Phi interactions, which was never observed so far. Are there questions or comments? Okay, Parada, please go ahead.
Yes, thank you for a nice talk. Yeah, I was just asking if you compare the coupling what's coupling? Sorry, pi with the. Can you come back again? Sorry, I forgot the coupling.
Sorry. Yeah.
Yeah. The coupling.
This one, right?
No. The last one. The coupling.
The value of the coupling.
The value of the coupling.
Okay,
yes.
Okay.
Yeah. Yeah. Pi n. Yeah. Pi n. If you compare with the SU, is this coupling has been used to produce, for example, equation of state in neutron star, something? No.
Not yet. I mean,
not yet. Okay. So but if you compare with the SU3 or SU6 symmetry, it is larger or
no, it's
a little
smaller.
bit smaller. Yeah. Okay. Thank you.
If you think about G and N, it is much smaller.
Right.
Meaning that in these models where this coupling was considered, so basically if you go to the beginning of the talk,
yes,
where you showed the RMF models,
right,
and you have these let's say repulsive, so you see okay, G lambda,
yeah,
2 times 2 square root of 2 divided 3 G omega n.
right.
And now our G pi n, okay, here it's not written the
0.0.
so, but it's anyway, it's something which is smaller than 1 because it's 0.13. So it should not. Well, we have to see what comes out. It has not been used. Now it can be used in this kind of.
I think it's better to check.
Yeah.
In the equation of state, I mean, yeah.
It should be less stiff, I think.
Right.
Yeah.
Okay, thank you.
Okay, other question or comments? Okay, if not, it's not the case. Thanks a lot, Emma. Then we go to the next talk, which will be given by Georgios about investigation of S minus equal minus 3 sector with interaction. So we see your slides, Georgios. Thanks a lot.
Can you hear and see also me?
Yes, also. Yeah.
Okay.
Go ahead.
Okay. Good morning, everybody, and thank you also from my side for giving me the opportunity to talk in this workshop. Yes, I'm going to, together in the next 20 minutes, we are going to explore further the hadron-hadron interactions, this time in the STRANGeness -3 sector. In particular, I'm going to show you the results which the first ever measured proton omega and lambda psi interactions, where the proton omega interaction is also the first ever measured interaction in the STRANGeness -3 sector. I want to focus also in the point where those two interactions are connected to each other via the coupled channels, and how the results of the lambda psi analysis influences the interpretation of the proton omega analysis. Both the proton lambda and the proton omega and the lambda psi analysis play a role in solving the hyperon puzzle in neutron stars. But I want to focus on another thing here, which is the misalignment between experimental data and first principle theoretical calculations with lattice QCD. So experimental data on those hadron-hadron interactions come mostly from either scattering experiments or exotic atoms or hypernuclei, which cannot reach beyond the strangeness sector of -2, because going further, the involved particles have so small lifetimes that these kinds of experiments become unfeasible. In fact, beyond strangeness -3, we don't have experimental data until now. On the other side, the theory side, the calculations in lattice QCD are particularly stable for large quark masses. So if we want to test and verify the calculations from lattice QCD, we somehow have to reach into higher strangeness sectors. And with Phentoscopy, we can do exactly that. So in our group, we, as you now saw, we study different interactions with Phentoscopy, and we do that at the Alice experiment at CERN. because the Alice detector has very excellent particle reconstruction capabilities. Both analyses I'm going to show you were analyzed from data from proton-proton collisions at a center of mass energy of 13 tera-electron-volt, and we pre-select high multiplicity events because there it was shown that there's an enhanced strangeness production, which is exactly what we need. The proton omega analysis was published last year in December in the Nature journal, which shows the great interest the physics community has in these kinds of studies. The Lambda-Phi interaction got its preliminary status just a few weeks ago, so both results are very fresh and new results, which I'm going to present now. I will summarize only the most important things of the Phentoscopy method because we saw it already in detail in Rafael's talk earlier. So the central part is the correlation function defined in terms of the relative momentum of the two particles we want to study in their pair rest frame. And in order to calculate it theoretically, we need two things. We need the source function, which is a probability distribution for the two particles to be emitted at a relative distance r star, and the two-particle wave function, which contains the interaction potential. As a reminder, how the interaction translates into the correlation function, if we have a repulsive interaction, then our correlation function stays below 1. If we have an attractive interaction, the correlation function is above 1. And I want to highlight one particular thing. If the attractive interaction is strong enough to facilitate a bound state, then we can see that also in the correlation function by a depletion below 1. And this you can understand by the following. So if the two pairs we are studying form a bound state, then they are lost to the same event distribution. So we count effectively less pairs, and this causes the depletion. Also, a small remark, every time I talk about proton omega or lambda psi, implicitly the antiparticle pairs are also considered because they have the same correlations. So the proton omega correlations are the same as the antiproton anti-omega, and the same for the psi, just to keep that in mind. Only a few words to the source function, because also that we saw in the talk of Rafael in the morning. We use a Gaussian function for the source function, and for that we need basically only the source radius, which we can get from out of the data we are analyzing by calculating the averaged transverse mass. From that, in the end, by considering also the strongly decaying resonances, we get an effective source radius, which we will use for the analysis. The correlation function itself does not only contain the genuine contribution we are interested in, but it has also different contributions, which I want to explain here a bit in detail. So first of all, we can factorize the experimental correlation function into a non-femto and a femto part. The non-femto part dominates the correlation function for the K-star region above 200 mega electron volts over C, where no phentoscopic effects are present, and where we would expect that the correlation function approaches unity. The measured one does not, because their energy conservation effects play a role, and this we have to describe phenomenologically. The femtoscopic correlation function itself contains also different contributions, starting with the genuine contribution, the one we want to measure. Then we have a background contribution from misidentified particles and a feed-on contribution, which I want to explain in this example. Imagine you want to study the proton omega correlations. Then you go to your events and you measure omega particle and a proton particle, and you pair them in order to calculate the relative momentum K star. Now, if the proton is a decay product of, let's say, a lambda particle, what you actually measure is not the proton omega correlation, but not the proton omega correlation, but the lambda omega correlation. In both of the analyses I'm going to show you today, we assume that the feed-on contributions are flat because the interaction we would measure is washed out because of the decay kinematics, and this is not visible within our uncertainties. The lambda parameters you see here say as to how much those contributions contribute to the femtoscopic correlation function, and they have to add up to 1, of course. This brings us already to the results, and I want to then the analysis, and I want to start with the proton omega. What we have to do is basically to measure the proton and the omega particles. The proton is measured directly by the Alice detector, the omega not, because it decays before reaching the actual detector. So it decays into a kaon and a lambda, and the lambda itself decays into a proton and a pion. So the Alice detector measures those three particles and reconstructs the omega particle. As I said in the beginning, it can do it with it can do it very efficiently. So we have a purity of 95%, which means that only 5% of all the omega candidates we have are fake contributions. To give you a sense of the statistics we have, so in total we have 0.6 million proton omega pairs, and in the K-star region of interest, so below 200 MeV, where the femtoscopic effects play a role, we have about 4,000 events. 4,000 pairs. Okay, let's put everything together we need in order to extract the interaction. So for the femtoscopic correlation function, we have about 80% contribution of the genuine correlation function, which we calculated. We got the results from the Lattice whole QCD collaboration, Lattice QCD calculations. The background we will model with a third-degree polynomial, and it contributes with about 15%. And the feed down, which I remind you, we said it will be flat with 6%. The non-femtoscopic baseline we will model with a constant function and a first-degree polynomial. The variation we use as a systematic variation. And the source function, in the end, what we extract is 0.95 femtometer by the process Raphael explained in his talk. Putting that all together, we can actually extract out of the experimentally measured correlation function the genuine correlation function by correcting all the other effects I told you. And this I show you here. So in the data points you see is the genuine correlation function. So you can actually compare, as soon as you have a theoretical model of your correlation function, you can directly compare it to these data points. And the comparison here is theoretical calculations, but assuming only Coulomb interaction between the proton and the omega. And what you see very clearly is that it fails to reproduce the data. So there is something missing. Only Coulomb is not enough to explain the data, and that thing what is missing is the strong interaction. So here you can actually see that there's an attractive strong interaction between the proton and the omega. And before showing you that, I want to spend a few words explaining how they are calculated in Lattice QCD. So the proton, being a spin one, has a spin of 1/2. The omega has a spin of 3/2. So together they can couple into either a spin 1 state or a spin 2 state. And the spin 2 state can be calculated in Lattice QCD. You see the result of the potential on the right. The spin 1 state is a bit more complicated because in principle there, those coupled channels could be present where the proton omega couples by respecting all quantum numbers to the lambda psi and sigma psi system. And the problem is that it's not known how large those inelastic contributions are because they depend on the interaction between the lambda and the psi or the sigma and the psi. And this is a STRANGENess -3 system. And remember, we don't have so far any experimental data on this. So the only thing we can do is we can discuss two limiting cases. So either we assume that the coupled channel is negligible. So the spin 1 state is like the spin 2 state, or the coupled channels are dominating, which is the second case. And both of them are showed now here. So in orange, the assumption that the coupled channels is negligible. And in blue, we have the assumption that it's actually driven by the coupled channels. Let us notice first that the accuracy of the data is higher than the accuracy of the theoretical calculations. Then we notice that we have a better agreement for the theoretical calculations where the coupled channels are negligible. And the third thing that we see is, and you see this better in the inset of the plot, that as soon as we include the strong interaction, it predicts a bound state, a proton omega bound state with a binding energy of around 2.5 MeV, which is not reproduced by the data. So this has to be further investigated from the theory side. They can now adjust the calculations to reproduce the data, and we could try to study the dependence on the source size. But this would, yes. And in order to draw further conclusions, of course, we have to measure those the interaction strength of the lambda and xi, or the sigma and xi. And this is what I want to do now. So let's go to the lambda xi analysis. Also here, the lambda and xi are not measured directly in the detector, but their decay products are. So we know how the lambda decays. The xi decays into a pion and a lambda, and the lambda again in a pion and a proton. Again, we reconstruct those particles. And here you see already a challenge of this analysis, that was that we don't want, the lambda appears also as a decay product of the xi. And what we don't want, or what we should not do is to, we should not pair the lambda with its own mother xi particle, because those are of course correlated. In the correlation function, you would see this as a huge peak dominating basically everything. From this peak, we cannot learn any new physics, and it overshadows the interactions we are interested in. So we have to be very careful as to not pair those together, but only pair unknown xi's and lambdas, but from the same event. Also here, some statistics. We have 1.1 million events in total, and about 5,000 in the low K-star region of interest. Let's summarize also here everything we need to do the comparison. So the genuine correlation function contributes about 36%. We will model it with the Lattice model. More on that on the next slide. Then we have the background, which contributes about 8%, and we will model with a second degree polynomial. And we have the flat contribution, which is all the phaeton contributions with about 56%, which again we model as flat. The non-femtoscopic baseline is modeled with a shorter pole 2 polynomial and third degree polynomial. It's shortened like this because we want to ensure that it is flat in the K star equal to 0. It's the same we used also in previous analysis in the lambda-lambda analysis. And we use it also here. The source function, the radius we expect is 1.03 femtometer. And we can put this again all together, but this time we didn't extract out of the data the genuine correlation function. We went a different path, and we corrected the theoretical calculations by adding all the contributions I explained to you now to the theoretical calculations. So keep that in mind when I show you in 2 slides the result. It's not directly comparable to theoretical calculations. You have to add to the theoretical calculations those contributions here. A few words on the Lattice model we use to model the theoretical calculation. So it's an analytical approach in order to study final state interactions and build the correlation function. And the only thing you need for that basically is the effective range and the scattering length. And these we were provided by the theory. We plugged it into the model and calculated the theoretical correlation function with all the contributions, as I said. And here you see the first comparison. We did 2 comparisons. First, we compared to calculations from chiroeffective field theory to leading order. The data points are the correlation function, and you see already that it's rather shallow. We have a very shallow interaction of the lambda and xi. In contrast to the predictions of the chiroeffective field theory, which predict a rather strong attractive interaction. Actually, we were provided the calculations you can find in the paper of Heidenbauer and all. for 4 different cutoff values. And all of those calculations are included in the band you see here. So we were able to calculate an upper limit and a lower limit for the n sigma. So our n sigma range is between 2 and 8 n sigmas. It's a bit in more detail if you're interested here, just to get a more qualitative feeling of how the compatibility is with theory. So bottom line, our experimentally measured correlation function does not support this very strong attractive interaction. In contrast to the meson exchange model NSC97A from the Neutron group, which has a much better compatibility with our data, the n sigma we calculated is between 0 and 1, and you see it also in the plot here. It has a much better compatibility. Summarizing, again, we see a shallow lambda psi interaction, and this with this we are able to give first constraints on the calculation for the proton omega coupling. So it really suggests that the coupled channels to the lambda psi system is negligible, which is the first time actually that this is has been measured. And this brings me already to the summary. So I showed you today the first experimental constraints on the STRANGENess -3 sector. First of all, the first observation of the proton omega interaction, which we published last year in Nature. It has we confirmed the attractive strong interaction as calculated by Lattice QCD. We could not see in the data the depletion due to the bound state. And the theory is still missing the spin 1 channel, which we for the first time with the lambda psi interaction were able to constrain at least the coupling to lambda psi. Okay, the outlook, we want of course measure also further interactions, and we are eager to compare them to also to first principle calculations, and of course run 3 and run 4 will provide more data, even to do more differential studies. And I want to leave you with a humoristic visualization of what we did with Phentoscopy. So we really breached the we breached into the STRANGENess -3 sector, as you see here with the Phentoscopy method. Thank you very much for listening.
Thanks a lot, Georgia, for this nice talk and these funny conclusions of your take on the methods and let's say efficiency of the method. So are there questions or comments?
Can I, Laura?
Yes.
Thank you, Georgios. Really impressive results. Just a stupid question. I didn't get, how did you manage the lambda psi in lambda psi channel, the combinatorial background?
What do you mean?
The background due to the decay of the psi, I mean.
How we band this, that we don't pair. You mean this, that we don't produce this pair?
Yes, thanks.
Yes, the Alice detector, when it reconstructs the particles, it assigns an identification number to each particle. And what we can do is we can compare directly the decay product of the lambda with the decay products of the psi, and then see if they match up. And if they match up, if they are reconstructed of the same particles, then we know it's probably a daughter.
Okay, thank you so much.
Other question or comments? Okay, if it is not the case, thanks a lot, Georgios, again. Then we move to the last presentation of the day, which will be given by Parada.
Yes, okay, thank you.
And he will talk about chaos within nuclear medium and actually electroweak properties.
Yes. And
Okay, we
chaos.
can see your slides. Very good. Yes.
Okay, thank you very much for having me in this workshop. I'm going not to talk about the correlation function. As a previous speaker, most talk about the correlation function, but I talk about the electroweak properties of the kaons. This is my name, Parada Hutaru. I'm from the Department of Physics, Pukyong National University. Maybe all of you know or not know. And I'm this talk based on the this paper with Yongsuk or Kazuo Tsushima in the PRC, and also our paper in archive in this archive. So the outline of my talk is I'm briefly start with the pion and the kaon properties. Even that my title is only the kaon properties, but in the case I just added the simple one, the pion properties in the beta salpeter equation Nambu-Jonah-Lassina model. And then for including the medium effect, use the Clockmason coupling model. As I will mention, I will also explain this model. And then, we try to, I will show you also the pion and the kaon properties in nuclear medium, like a mass coupling, quark coupling of the pion, and also pion decay constant. And the next, I will also show you the pion and the kaon form factors in nuclear medium, which is the structure of the hadrons. And at the end, I'll try to make a conclusion and outlook. Okay, these are some introductions. Start from as we know, the pion was introduced as all the speaker talking about the nuclear interaction or high-front nuclear interactions, mediated by Yukawa interactions in the strong force. And the other things, there's a perspective. The pion is a Goldstein boson emerged from the consequence of the spontaneous breaking global chiral symmetry in the flavor SU2, has a special place in QCD, like a NGL model. NGL introduced like a chiral symmetry and is breaking for generating mass and appearing pion. So all of this you can see in this paper. This Nambu, this Jonah-Lassina, which is a proposed NGL model. And then this is just illustration how to show you the global symmetry spontaneously breaking. And in the market, there's have been many studies devoted to understand the internal structure of the pion in the free space using several phenomenological model or approach, such as NGL model, instanton vacuum, light front, and Dyson swinger models, also as well as lattice QCD simulations. And as you see, the picture is a prediction of the structure of the pion using the phenomenological model, and also this one using the lattice QCD. But however, in the nuclear mediums, only few theoretical studies have been reported so far on the pion and the kaon structures, and no experimental data available. In the past, some study has been done only for nucleon in the medium, which is correlated to AMC effect. Another recent work from this paper, Melo, the Brazilian group, used electron constituent quark model to describe pion in the vacuum and as well in the medium. But they're using the electron quark constituent quark model, which is Dirac mass value in vacuum is input treated as a parameter, but there's no quark condensate in this model. So we address this point in our work by using the NGL model, which describes spontaneous breaking of the chiral symmetry and offers dynamical generated quark mass through quark condensate. So some observations such as AMC effect indicate the internal structure of the hadrons may change in the nuclear medium. So these phenomena of the medium modification is therefore a more interesting subject in nuclear and hadron physics. More detail about this one you can see in this paper, G. Brown paper, Sato papers, and also Hayano. And also the interesting thing is that chiral symmetry has a big impact in the low-lying hadron mass, as we know how the generating hadron mass by breaking chiral symmetry breaking, and the partial restoration of the chiral symmetry is strongly interaction medium and important to understand the change of the hadrons properties in nuclear medium. So the other things, pion is it's a very simple structure, which has a bonds that compose address quark and antiquark pair, like this picture, and this for the baryon, and this meson molecule, like some speaker has been discussed about this one, and also the tetraquark. And in this case, we take a simple one, which is a focus to electron properties in nuclear medium for meson, and then we can calculate the weak decay constant in medium, and also pi and quark coupling constant in symmetry, nuclear matter, and quark condensate. So, okay, that's an introduction. So these are the formalism that you use in, we call it the beta submeter NGL model. The trip-level NGL model, Lagrangian, we can write down like this one, which is contain only 4 fermion interactions. And this the kinetic part, this is the interaction part. This is the quark field and the flavor components, and this 4 fermion coupling constant. So this is the for the scalar one, for the rho, the factor one. So this is the Gell-Mann matrix, lambda 1 and 2, 8. And this is the mass of the current quark mass matrix. So in the NGL model, this very simple model, which is the gluon exchange, is replaced by 4 fermion contact interactions by integrating out of the gluon field and absorbing into the coupling constant. That's you call it a quark effective theory. So this diagram is illustration how the gluon absorbed to the coupling constant is like this one. So in the NGL model, they use this one. But the problem is the NGL model has a lack of confinement. So it can be seen very simply, is seen in the quark propagator has a pole. So therefore, we have to regularize using the proper time regularizations that we call it also can be simulate confinement. More detail about this regularization you can find in this paper. So what in the proper time regularization you can use this is the propagator. Then we can translate it to such kind of this one, and then we determine the infrared cutoff, which is close to lambda QCD, which is with the value is 0.24 GeV. And then lambda UV we can determine by fitting to the pi and deco constant and pi mass. And how the NGL model that we calculate the gap equations are determined by using the propagator, quark propagator in the momentum space is like this one. And then this we can calculate the dress by this the bare one, and then this there's a propagator and the loop interact with the vacuum one. So from this one we can interpret it, and we can get the mass of the gap equations like this one. So and then this correlated with the quark condensate, chiral quark condensate we express like this one. Okay, as a function of the mass of quark mass and in the proper time. So in this case, mass is generated through interaction with the vacuum. So the quark condensate is not equal to 0. So this is the result for the mass. These are the quark mass in the free space, and this is the coupling. So if you can see in this result from the NGL model, this from the Dyson-Swinger equation model, you can see clearly here how the mass generated, quark mass generated inside the pion. So this one without momentum dependent, this with the momentum dependent. We compare with this one and the NGL model, we can conclude that NGL model can be used for low momentum P and low energy. Okay, so we know the pion and the kaon is not is a bound state. So to perform the bound state, we can solving using the Bethe-Salpeter equations. It's like this one using the in the angel model. The T matrix is very simple, and then you can use interpret this payment diagram. You become like this one, and then the solution for Bethe-Salpeter equation in the pion and the kaon, we can perform like this one. This is the gamma 5, and this is a T matrix, and then we can take the T matrix as a function of the G pi, and then this polarization insertion for the pion. For the Robinson, you can express like this one. So the bubble diagrams appearing, which is in here in the equation 5, we can interpret it like this one. So integrate, there is a pole like this is the propagator, and this is the vertex, gamma 5, and this propagator. And the for kaon is the same thing, but we can changing with the light quark with the strain quark. As you know, the kaon is contain up and the strain quark. So this for the vector meson. And then from here, you can calculate the mass of the pion and the kaon using the given by the pole T matrix by using this one, and then you can get the mass of the pion and the kaon. The expression for the kaon mass, kaon and the pion mass, you can give like like this one. So it's a function of the mass of the kaon is a function of the strength, the quark mass. So in the proper time, you can express this symbol, or miss like the one, but yeah. So you can use express like this one in the proper time. So from here, also from the pole, we can also calculate the residue of the pole using the Q bar T matrix in with a effective meson coupling meson. You can get it by derive the polarization insertion against the momentum square, and then close to the in the on cell. So, and the pion and the kaon decay constant, you can in the proper time you can express like this. So okay, now I'm talking about the Clockmason coupling model, which is also the effective Lagrangian for the symmetric nuclear matter in QMC. This is the kinetic part is the omega, which is the factor one, and this is the meson Lagrangian, free meson Lagrangian, which is this sigma, this omega. So in the QMC, the nucleon is not a point particle, but is has a structure like using the back model. So inside the proton, there's a 3 quark valence quark inside using the using the back model. So more detail about this one you can see in this paper. So in the KMC model, the nuclear matter is treated as collection of the nucleon that are assumed to be non-overlapping MIT bags. The direct equation for the light quark inside the bags, you can write like this one. This for the U quark, this omega potential, this rho potential, this sigma potential, scalar potential, and then this for D quark for the S quark. And then the effective mass, current quark mass from this one, you can calculate it using this mq square equal to mq, which is the current quark mass with the potential of those sigma potential or a scalar potential. And yeah, so and the effective nuclear mass you can calculate it like this one, and then using this one you can by feeding this one to the saturation density energy, and then you can find the coupling for G sigma, this one G sigma G omega, and this the back constant, and you can nuclear mass and then compressibility. This one is a standard one, but this one we take it is now the quark current quark mass is the same like in the NGL model. And then this the energy binding with the density, And then you can see here they produce is around 0.6 and 0.15 Fermi. And then this is the mass of the in the medium, in the QMC. So okay, now we go to pion and can properties in nuclear medium. In the medium, using the properties from the QMC model, we use the current quark mass 16.4 MeV, which is calculated in the NGL model. And then we calculated the effective mass mu as a function of density in medium ion decay constant in the NGL model. In the medium free propagator, we change it the propagator by edit the potential, and the mass is the current quark mass, the effective mass of the quark, and like this one, the propagator. So in the medium propagator, we shifted the momentum using k mu plus the vector potential. And then in the medium NGL get mass in the proper time, we can get like this one. More detail about the number of this explanation you can see in this Miller paper. And the result for this for chiral condensate as a function of density, which is rho 0 is 0.5 Fermi minus 3. And then you can see here the ratio of the in medium to vacuum quark condensate is a decrease with the increasing nuclear density. So the saturation density is estimated is a 0.87. So this somehow higher than obtained by Gido, which give you 0.6. Sorry.
It was the telephone of somebody else. Go ahead.
Yeah, sorry. The rest is one for 0.72.
I don't see any microphone on, so.
But it's you, Parada, who has this.
Yeah, because there is no other.
Yes, sorry.
So
Okay.
Can you move?
Can you hear me? Can you hear me?
Yes, we can hear.
Okay. Sorry, there's a distraction. I mean. Okay. So this now the quark condensate, and now I show you this one the coupling pi and quark coupling constant. The ratio in medium to the vacuum pi and quark coupling constant against the density, and also decreasing, which consistent with the result with the Perenica-Bernoulli. At normal density, we obtain this 0.77, which is smaller than the value of obtained in the Romanjo papers. And we also calculated, as I mentioned before, we calculated the ratio of the medium to vacuum pi decay constant as function of the density, which is the ratio is found to be decreased as density increasing. At normal density, which is the ratio is 0.87, which is good agreement with the Kindler papers, which is 0.80. And the ratio is larger than the values obtained in the 9 and 10, which are Kirchhoff and Messner paper. It's about 10 to 20%. For the pi mass, and then you can see here the pi mass is changed up to almost unchanged up to 1.25 rho 0, which is consistent with the result obtained by Bernard in the low density region. So this that we got for, and then the difference between the in medium and the free pi mass is 6% up to nuclear density 1.25 rho 0. This justifies the assumption deeply bound of pionic atom that which is the pion mass in the medium is equivalent to free mass of the pion at normal density or 1.25 saturation density. So the ratio of the in medium to the vacuum isofactor nucleon, also we calculate that one, and then we can get the result is a GA in medium. The ratio GA star with the GA is 0.99, which is consistent with the quenching of the GA star, but less amount of quenching compared with the result with the LU that give us GA star divided by ratio of the GA star and GA is 0.9. So after we calculate the properties, we can also calculate the medium modification form factor of the pion. So in the form factor, we calculated, as you know, the pion consists of the UN down quark, and then using that one, we can describe using the this Feynman diagram contribution, which is the photon kick the up quark, the up quark, or the photon keep the down quark, and the complete one you can interpret it this Feynman diagram for the pseudo-scalar Mason form factor by using like this in media. So it's almost the same like in free space, but you can just only the quark mass change it and the coupling change it as you use in the medium. So the result in the medium space like a form factor of the pion you can see in this paper already published in PRC, and this like this one. If you increase this for free space and increase the density 0.25, 0.50, 75 on 1, and you can see the form factor of the pion is decreased against the momentum chi-square. So if you see this one chi-square times the form factor of the pion, and you can see also how that the decrease against the chi-square when the density increases. So the medium effect of the suppression of the pion form factor are clearly seen, and it's reduced 20% at normal density, which is would be large, be extracted empirically. Okay, so using that from the pion in the medium pion form factor, and then we can calculate the charge radius of the charge pion in the nuclear medium and its quark sector charge radius for, as you see in this table. So you can see like rho b for rho 0 is a 0.25, and then you can see how the charge radius of the pion change it. This for the free space compared to the experiment, it's not it's good agreement. So, and then this for the up quark, which is in the pion we take the U and D quark is the same, so it is D also the same charge radius. So we obtain the charge radius of the pion in the vacuum is a good agreement with the experimental data that I mentioned, but we cannot compare with the in medium because we don't have the data for this one. This form factor for the kaon, form factor, which is this for the kaon. So the red one is for free space, and the blue one, the dust long dust blue is 0.5 density, and this one, the dot one, is a 1 density saturation density. And then this is for the kaon, for this from the up for the up quark in the kaon. So you can see like this one, and then if you this is the strain quark in the kaon contribution, and then this the chi-square time form factor of the kaon. You can see like this one. So in our kaon form factor result, decrease is increasing density as a prime case. As a and then the result in the medium space form factor of the kaon, this compared with the experiment, which is the only data that we have now. So this is in the free space, and you calculate like this, And then you can see overlap. The data is very good with our theory prediction. And we increase the density in 0.5, and then you can see here how they change it. So our current form factor is decreased, as I mentioned before. So this result you can see in this paper. So we also calculate the same thing like a pion. We calculate the charge already of the charge kaon in the nuclear medium and the quark sector already, and then you can see here in the table density. It is the kaon radius. This is the up quark radius in the kaon. The string quark radius in the kaon. So this is the experimental data. So you can see that one. So this is the conclusion that we have studied kaon and pion properties in the vacuum as well as in the medium. Our prediction in kaon properties are good in agreement in the other prediction. We have extended our study in the medium modification form factors and the kaon in order to get the picture of the form factor of the kaon in the medium. The result is really look interesting and promising, but unfortunately, we need experimental data to test our prediction. And this work will be interesting to extend calculation to Parton distribution function or generation function or Parton distribution function of the pi and kaon, rho meson, D and B meson in medium, as well proton and nuclei. Okay, thank you very much for attention.
So thank you for your talk. Are there questions or comments? I had one because in the end, you, let's say, ask for experimental data where word is in medium measurement of the decay constant of pion via pionic atoms. About
the properties, maybe we have some calculations, right? But for the form factor, maybe I don't know. That's
no, for the medium modification of the decay constant of pions.
Oh, okay.
There was a measurement, pionic atoms.
Pionic atoms, yes.
Yes. If you compare these results to your calculation, what do they agree? Okay, here I see.
The mass is agree, yeah, I think so.
Yeah, but F pi is a bit larger.
F pi is a bit larger, yes, right.
But because it was 0.67 for that they used.
Right.
Yeah, okay.
But compared to the Kinley papers, it's a 0.80, right? So.
Okay, I see. Okay, so it's in agreement. Thank you.
Yeah. Mm-hmm.
Any other comments or questions? Okay, if it is not the case, I would like to thank you for this nice talk and all other speakers of this session.